Yo, 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 what's up? Hi,
Hello,
everybody.
hello.
Welcome.
Lovely, lovely.
Oh, yeah. Hi, Edwin. What's up, man?
Hey,
How you doing?
good to see you folks. Thanks for putting this on.
Yeah.
No
Thanks for
Yeah, good to
coming and
see you
having
here.
cool art in the background. That's nice.
Oh yeah, thanks. That's something I had made for a Yuri's night years and years ago in LA.
Yeah,
Damn,
That's
that's
a
awesome.
tiny little spacecraft up there.
Oh, that's cool.
sick.
Nice.
Yeah, so
What's
Kerry,
up?
the thing that was like really interesting about it is that there's like for gas tube lasers, this I was telling Kerry that I helped work on the a power supply, a high voltage 25 kilovolt power supply for gas tube lasers. And
That's a lot. It's a lot of
what's-
volts.
it's a lot of volts. And
Yeah.
what's really interesting about them is that you have to break the gas down. So you have to have enough stored energy in the output stage of this power supply to break the gas down so that it will start conducting. And that happens at like 25 kilovolts, but then the voltage just crashes as soon as that happens, and it drops down to like 7 or 8 kilovolts. So you have this very rapid swing in the output voltage, and your transformer has to keep up with that. And it was really hard to get it right. So you have to tune your output capacitance to be just right to get things to work. It was super complicated.
What was the topology? Do you know? Was it a switched capacitor?
I don't think I'm allowed to say what the output topology was.
Okay.
I can't say it was not. It was not a flyback, and that the output efficiency was like 98% or something, which is pretty.
That's amazing.
98.
Yeah,
Jeez.
yeah, it was really high, and which is great. But yeah,
Well,
the trick was
hopefully Kerry can get us to that level of efficiency in the session.
Right?
I don't know. I was gonna say I bet you it's switched capacitor, because when we bootlegged, we needed a welder in college, and we couldn't afford one, so we bootlegged a bunch of capacitors and then used that switched capacitor bank to bootleg a welder. So I got to imagine it's something like that.
Yeah. Well, there's definitely
You don't
the
have to
output
answer. It's
capacitance.
okay.
I honestly don't know if I can or not. I don't know where the patents are on that. But
For those of you that don't know, Jared here at Flux, we employ actual scientists, actual physicists. So that's what we've got going on here.
Anyone who works with lasers is an actual physicist.
That's
That's how you get the
science.
title.
I don't make the rules. Okay.
That's how you get the
I don't
title.
make the rules. That is. Welcome, everybody. We're just waiting for people to file in here before we officially get started. Isn't that right?
Yep. Just
Right.
chatting a little bit, getting to know the people
we'd love
joined.
to know where you're calling in from. If you feel comfortable turning on your video so we can see what kind of cool miniature spacecraft you have in your background, just like Edwin, or just say hello if you want to unmute.
Or if you've worked on a cool power supply project, tell us about it.
Hello.
Hello.
Hi, John.
Hello. Did a 1,000,000-volt fast swing flyback power supply for a scanning electron microscope once upon a time.
Oh my
That's
goodness.
cool. That's really cool.
I don't know if I have anything
Fill
to
it with
teach
mineral
you.
oil.
Oh yeah. That's awesome.
This just in, Edwin is going to run the session today.
Yeah.
So
That was a long time ago. No worries, Victor. It's not necessary for the event, but those who have the camera are welcome to turn it on.
Did you want to hear about another project?
Oh my God,
Yeah,
yes,
absolutely.
dude.
Man.
Oh,
What you
yes.
What are
got?
you waiting for? Lay it on us.
All right. So I run a nonprofit tech mentoring program for disadvantaged teenagers, and we're developing a hardware product so that we can engage our teen apprentices in building and selling an electronic device.
Oh, cool.
And so in the process, we're developing some original technology. We just got a first provisional patent on a mechanical device that I designed.
Awesome.
And I worked with an EE to develop what we think is a novel battery charging system. I can't share too many details, but It's a system that would enable you to charge and balance a pack of multiple cells in series in the same time that it takes to charge a single cell.
Oh wow.
And
That's cool.
we're looking for some experienced DEs who know about DC conversion, who would like to do some volunteering and prototyping with us. It's called theboom.org.
The boom.
This is a great place to
Boom.org.
ask. In our Slack, we
Yeah,
actually have
absolutely.
a jobs channel where you can post that info, and there's a bunch of people there that have a ton of power supply experience. That might be a good place to go.
Awesome.
Yeah.
Where's that?
Yep.
Where's that page?
It's on Slack.
We're gonna drop that link in the chat.
Awesome.
Yeah.
I'll put my
Like it.
website in the chat too.
So thanks
Yeah,
for the
that's
segue.
great.
I just pasted the link to join our Slack community.
Perfect. You beat me to it.
Oh, John, are you based in the Bay Area?
Yes, the project is in the Bay Area. We're focused on Bayview Hunters Point, but we want to expand to more cities and countries.
Awesome, dude. I'm calling in from Oakland today.
Awesome. Awesome. Oakland's our next stop.
Oh, that's great, man. Wow.
Right.
Okay,
I think
Nico, what do you
can-
say? Yeah. Let's do it.
Exactly. I think we can get started.
Let's do it.
So we're all hyped about power supplies. Which it's the purpose of this very session. So we're going to be talking about power supplies a little bit. So first, let me introduce myself a little bit. So I'm Nico. I'm a product ambassador here at Flux. I am in charge of trying to make people enjoy your experience while starting out. Make sure that you have project examples, documentation, things like that. Build projects, see what other cool projects you guys are building. So I would love to hear either stuff that you are building in Flux, outside of Flux, or you even plan to build on Flux, so I can help you out, connecting you to the right people. We have a great community that I just shared a link. So a Slack community, there's a ton of people there sharing what they do, asking for help, design reviews, stuff like that. And we also are running a competition on energy harvesting that I'm gonna share a little bit more about at the end of the session. So that's a little bit about me. And in this session, we're talking about power supplies. And for that, we brought Kerry in, and he's a former iPhone engineer. And he promised to tell a story about power supplies and why he's interested. But he didn't tell me what story was that. So I'm a little bit of curious to hear what that story is. So I don't know, Kerry, if you want to introduce yourself a little bit.
Yeah, definitely. I don't think the story is as cool as Jared's or Edwin's because it doesn't involve lasers. But as Nico mentioned, I've been in the electronics industry for 10 years. I was on the iPhone team at Apple from 2013 to 2018. In 2013, I was an intern, and I was going through it was like 8 months into the internship. And I was going through the process of interviewing for full-time, and there was 12 of us, and we were all fighting for like 2 spots. And so it's like really nervous about this whole thing. And the manager at the time asked me a question about like, how would you design your power supply infrastructure? When would you use an LDO and when would you use a buck? Literally the conversation that we're going to have today. And I did not know. And I just basically made up a bunch of stuff. And he was like, you need to do a little bit of a better job of knowing your power supplies and talking around the things that you don't know, which was not a skill that I had at that time. So that is the main reason why I am so excited about power supplies. The secondary reason is that working on the iPhone, I saw a bunch of really cool shit in terms of power supply design. When you have such a small area on the circuit board that's devoted to the power supplies, and they can push upwards of 30 amps, and your inductors are like 1 millimeter by 2 millimeters. It's pretty cool to be surrounded by that type of equipment and just the expertise that people had there. And I think power supplies are often a forgotten part of the system, right? Like we get excited about the microprocessors and all of the other stuff, but if your power supplies don't work, nothing else works at all. So yeah, exciting infrastructure in power.
That's great. So hopefully you learned your lesson, because one of the first things that we're going to be talking about is bug versus LDOs.
Yeah, you guys can judge me on if I've learned in the last 10 years or not.
Right. Yeah. So that's kind of going to be my next question. And I'm going to sort of show like the two circuits of LDOs and bugs, so you can sort of talk about that a little bit and try to sort of see in what cases you use one, in which cases you use the other one, why one is better for one use case or another. And again, like the frame of the conversation is like high efficiency. So we're going to be trying to find what the best option is for efficient circuits. And when we choose one option, we're going to try and go like over tips on how to improve efficiency for that option. So why did we start to talk about power converters and efficiency? So during our last event, which is like 2 weeks back, we talked about this specific IC, which is a solar energy management system. Basically takes power from a solar panel, puts it up in a battery or supercapacitor, and then feeds the load with that energy. The kind of like the pro and the con that this IC has. So the pro is that it's super simple. It's just one IC that it does it all. The con is that the power conversion sort of sub-circuit of this IC is not super efficient, and also having everything integrated makes it a little bit more expensive. So some people back in the event ask, again, like if I wanted to sort of separate the two stages, have one system that controls the solar panel and do the sort of power conversion separately, how would I go and do that? So that's why we're here talking about efficiency in power converters. So put it back to you, Kerry. Can you explain us a little bit like what the two main options that we have are, like how they work, and why one is better than the other one for this use case?
Yeah, definitely. Do you want to drop the link to this in the chat so everyone
exactly.
can join?
Do that. So I'm going to share the project that I'm looking at. Anybody can join here. And yeah, like you can take a look at the chat. If you have any questions, feel free to drop them in the chat, and we'll try and address that during the session.
It's so fun to see all the people in here, and it's nice to be able to gesture wildly and you can see it instead of screen share. Sometimes doesn't do the branchedness of the gestures any justice. So on the left here, I guess at a high level, power supply selection is so important for whatever it is you're trying to accomplish. It sets so many goals of your system. Like you want to hit a particular efficiency target, you want battery life, you want any number of things to hook up to a solar array, and so you need to figure out, you need to be able to handle a really high incoming voltage. And so all of those things relate to the power supply selection. I think that not a ton of people pay a lot of attention to power supplies. I see a lot of people who don't have a ton of experience in the industry just using LDOs for everything. And those are great. They're very easy to implement. And I use them sometimes when maybe I shouldn't, because I don't want to implement all of these extra parts or whatever. But there are reasons to use them and reasons why you wouldn't want to use them. So on the left, we have an LDO, and on the right, we have a buck. An LDO is what's known as a linear regulator. I often call it a linear dropout regulator, but it's generally, I think, a low dropout regulator. And it's called a linear regulator because the way in which you drop the voltage you're trying to, it's a step down converter. You take, say, 10 volts, for instance, and turn it into 5 volts. The way it does that is it's a switch, it's a MOSFET, and it changes the resistance of that FET. It has a controller inside of it so that it just burns off that extra energy that's coming in at 10 volts. And that's how it gives you 5 volts at the output. it has a very fast response time, and so sometimes you get much faster load regulation from an LDO than a buck. But you also, since it burns that extra power, you lose a ton of efficiency. And so if you're dropping 10 volts to 5 volts, you have 50% efficiency. That's always how LDOs work, and you can't do any better than that. So in that way, it's really good to use LDOs for low drop environments. If you want to drop like 5 volts to 4.5 volts or 3.3 volts to 3 volts, those are good opportunities to use LDOs. If you have a low power draw, then you also maybe don't care so much about efficiency. If you're only pulling 5 milliamps from the thing, you don't really care about an additional 5 milliamp efficiency loss if you're dropping 50%. And they're really clean. You get really clean power out of them because you're just dropping that energy over the resistive element. There's a term called, I think it's power supply rejection ratio, and you'll see something like, I think it was 100 dBs. It's been a little while since I've been super in the weeds on power supplies. You'll see like in really high quality LDOs like 100 dB power supply rejection ratio. And what that means is if you have noise coming in, that noise on the output will be 100 dB less. And 100 dB is a lot. That is a lot of rejection. And so you'll often see LDOs used in really clean power environments. Like often if you use an analog to digital converter, you'll use LDO for the power supply for that, along with some filtering. So that's LDOs. I'm going to talk a little bit about bucks, then we can talk about maybe when you would use both together. So on the right, we have a buck topology. This is called a switching regulator, and there are a bunch of different classes of switching regulators. In order to be a switching regulator, all you really need to have is a switch. LDOs also have a switch, but that's used in a resistive capacity, and it doesn't generally turn off all the way. It's always conducting in some capacity, and that's how you get the power through. What makes the switching regulator so interesting is that there's an energy storing element. So we talked about how the LDO just burns power over the resistive element, and that leads to the power loss. In a switching converter, this inductor does a lot of magic, and when you pulse this switch, it will bring energy into this inductor. That inductor will store that energy in the form of a magnetic field, and then that field will collapse again, and that's what provides the charge out to the output capacitor. And so we talked about LDOs having a particular amount of efficiency that relates exactly to the amount of voltage that you're dropping over them, or the percentage of voltage. In bucks, you can drop any voltage to any other voltage and get 85 to 98, 99% efficiency. I think 99 is the highest efficiency that I've ever seen. And so we'll talk a little bit about how to improve that efficiency as well. I think that's our next topic. And then, so when you would use bucks and LDOs is, say you have a high drop situation. So I've worked on a lot of products that have input of 9 to 36 volts. That's a really wide range, and we need our system to run. We need a system voltage of 5 volts, 3.3 volts, 1.8, 1.0, whatever, to run all of our processing systems. But we also have super clean systems like an analog to digital converter, or the PLLs for your microprocessor. You need the power supply to that to be very clean. And so how do you do that? If you used an LDO, you would be dropping like 3 amps. You'd be losing 3 amps over this FET. And so that's going to get really hot. Your LDO is going to be half the size of your system in order to handle that thermal load. And so what you do is you use a buck first, and you'll buck across that wide input range. You'll buck it if you need, I think 3.1 volts is a common voltage for some of these analog systems. You might buck down to 3.3 and then use a really low dropout LDO, an SLDO, a super low dropout regulator. That's one of the things that you have to pay a lot of attention to when you're choosing an LDO is the dropout that relates very closely to the resistance of the FET, the RDS on, because if you have a high resistance channel, it'll drop more. And so if you want a low dropout regulator, you need to pick a low RDS on. Anyway, so that's how you would use LDOs and bucks and in what context and when you would use both of them. Usually it doesn't make sense to, there's a rule, to never buck a buck or boost a boost, but there are specific cases when you would buck then LDO or boost then LDO. And that depends on the requirements of your system. So that's sort of an overview of that stuff.
Great. So I think that kind of gives us an overview of some of the two systems and why would you choose one. I think it's clear that for the purpose of like energy harvesting and like try to be efficient with the energy, like the small amount of energy that you can harvest, that switching is going to be, like in most cases, the go-to option. So kind of what we want to move on now is to try and get an idea of, let's say that you have a buck converter. That's how can you design one that like takes the efficiency and try to extract the most out of that converter. So it's probably, there's probably, you can tell us more about that, but there's probably some inherent limitations on what each IC can do, depending on how the internal construction of that specific IC is. So every IC has a efficiency curve, but in order to get to the very top of that efficiency curve, like what are the things that we can do? So we have here a kind of like a standard switching converter. So I think, Kerry, would be great if you can sort of walk us through here, sort of how this is designed and what can we do, like either by adding, removing components, modifying values, or what are the things that we need to put the focus if we want to sort of try to get the most out of it.
Yeah, totally. I think that's a great point, that there's a lot of difference even within different types of bucks. Would you mind sending the link to that one as well so we can all jump in together?
I can drop it there.
Nice.
Sweet.
Thanks, Jared.
Yeah.
All right.
Can you hear me?
Paste the link with the HTTPS.
Yeah.
If you gotta paste
Oh.
it with the that was a
Come on, Zoom.
rookie move.
I think that project is not
There we go.
found.
There
Thank you.
go.
Guys,
Oh, and the
usually
privacy of the
can you guys
project.
hear me? This is Victor.
Yep.
Hey, Victor.
Yes. Hey.
Hey, eventually I managed it. I don't know what it was, but it wasn't working before.
Well, welcome to the chat room. And by the way, Nico,
Your permissions. Yeah.
Permissions.
Guys, usually it's Alex talking regarding the power supply. You can see LT Spice regulator and make some simulation. Usually LT Spice provides some model when you're doing some P-Spice simulation. Take a look what is exactly, and you can supply for like what is you expect, what is your input current, what is your output voltage, etc., etc. You can put this parameter and get proper power supply for like switcher or LDO, kind of this stuff. Yes.
Yeah, that's a really nice tool. I've used that in the past, actually. One of the things that scares me is designing a power supply from scratch. So taking a controller and sort of speccing out all of the components around it, doing the inductor selection, doing the MOSFET selection. And so I always use LT Spice or something like that to test out those components that I've chosen first before I go and build a board, because honestly, I have done all the math before and felt like I had a really good understanding of the parts that I needed, and then I went and built it and it totally didn't work. I think bucks are pretty reasonable. Like they have a pretty wide range of working values. But boost converters, especially high yield boost converters, I have to test those first, always.
Thanks for opening up the permissions there, Nico. So yeah, anyone who tried to view this project before and it didn't work, just give it a reload. It should be available to you now.
Yep. Sorry about that.
Yeah, no worries. So this is a pretty standard buck converter. We see a couple of major features that make a buck a buck. So the IC here, U1 is our controller IC. There are a lot of different criteria that different buck controllers have, and some of them have higher and lower efficiency. And so one of the things that you can do is find an IC that has a higher maximum efficiency. We have the inductor here. That is another core feature of what makes a buck a buck. And we have this diode. And so that's sort of how you know, well, really it's just the inductor that gives away what it is. And the inductor configuration tells you whether it's a boost or a buck. If the inductor has one connection to the IC, that's generally a buck. And if the inductor has two connections to both switches inside of the IC, then that's generally a boost. Let's see. So, sorry, just closing the chat. We want to talk a little bit about when you would choose different types of bucks and how those different things impact your design. So the different qualities that bucks have or different topologies, it mostly relates to this diode here. So this diode comes into play when the internal switch is closed, and it allows there to be a current path that allows you to have smooth current delivery in the system. There has to be some type of current path. However, when current is flowing across this diode, you're losing energy. And so that leads to your efficiency loss. You lose that to heat, you lose it to voltage drop inside the diode itself. Yeah, and so one of the ways that you can make that more efficient is using a FET instead of a diode, and that's called a synchronous converter. So you have a FET, of course, inside this IC, and then you can also have a FET that replaces this diode. That can be an external, it can be an external FET, but I found that the most efficient types of buck controllers have integrated high side and synchronous FETs. And so that's how you'll get the highest efficiency. I think this converter has maybe like 85% or 87%. And maybe we could look at some of the charts in the data sheet. But if you included a synchronous element, I think you'd get a lot more efficiency out of this. So let's talk about some of the other things. So there we go. This is a great efficiency curve. So you can see that the efficiency curve is pretty decent. We could make it quite a lot better by replacing that diode. You would need a different controller for that, and so that's one of the things. That's one of the reasons why you would need a different controller.
Just sorry to interrupt. I think the question in the chat is interesting while we're talking about that diode. So when you say that we want to replace that diode with a FET, like are you talking about a specific architecture of the FET, or like what usually people call like ideal diodes or like smart diodes? Like, is that basically making transforming that diode into an ideal diode, or are we talking about something different?
Yeah, I think ideal diodes are, someone can correct me if I'm wrong here, but I think ideal diodes are almost always FETs with a controller associated with them. Okay. Mm-hmm. So then when you see any type of, when you see a threshold voltage that you want to conduct, that will trip the FET to turn on. And that's why you need that separate little bit of a controller to manage that FET. I think those often have like a charge pump inside of them so they can give you full conduction of the FET, because if you just have a low voltage on the FET gate, then you won't have an ideal diode. You'll just have essentially a normal diode because you'll be dropping that current anyway, or you'll be losing that energy. And so, yeah, that's to replace the diode with an ideal diode. Ideal diode because FETs still have issues associated with them, because you'll drop energy over the channel of the FET. But you also need the controller for that, and the controller is related to the IC choice. And so if you wanted to take this IC and just add a FET to it instead of a diode, it totally wouldn't work. You definitely need a controller to be inside of that to drive that FET. I really like, this is from the time when you still had to make all of your own components. I always used bucks that had integrated FETs because I didn't want to go and find source and make the footprint for all of the different FETs that they wanted you to use. That's a little bit different in Flux these days because you can go in and most of the parts already exist, and so you can just grab them and use them, which is awesome. But I'm still like leaning towards some of my laziness, and I like the synchronous FETs and or the synchronous controllers with the integrated FETs, and also then that has higher efficiency. So it's nice that it's less work and it's higher efficiency. And that's because of a variety of reasons in terms of the parasitics of the path leading to the FET. Those are really small because they're integrated into the device and they have really tight control over the gate voltage. Those are some of the reasons there. So real quick, we'll just talk about some of the other things that you can tweak about your circuit. So say you could only use this controller. How would you make this controller more efficient? We already have a Schottky diode here, but if we didn't, we would replace it with a Schottky diode so we could have faster response and lower forward voltage. The higher the forward voltage of this diode, the more energy you're going to drop over it. And so you want that to be as low as possible. You want to use a pretty high inductance value. The inductance value is the multiplier between the charge and the voltage that's produced. And so for a given amount of charge passing through this inductor, you'll be able to produce higher voltage with a higher inductance value. And that's what leads to your stable voltage on the output. And your rapid response also in some capacity. The rapid response. So say you have a load on this supply here, and you're pulsing like 3 amps, and you want your voltage to be as stable as possible. You want to be able to produce voltage to replace that's being taken. It's not quite as simple as that. It's all just charge, and so you're relying on the charge that's stored in this capacitor. That's what's going to supply the load, and then you want to replenish this charge that's stored in this capacitor as fast as possible. So the inductance value is helpful for that. One of the other things that's helpful for that also has an effect on efficiency is your switching frequency. And so if you have a high switching frequency, you can replenish that, the maximum distance between the time at which you're taking energy from the capacitor and the time when the switch is open or closed, and it's going to replenish that energy through the inductor to the capacitor, is as low as possible because you have you're constantly sending energy through that inductor.
So Kerry, are you then like when you're like, if you're doing this, so you're kind of working like you're tuning those components together? Is that's right. Fair?
Yeah, and it relates a ton to your system requirements. I mean, I didn't realize this when I was much younger, but I thought it was like, I just pick a random buck or a random LDO and that's fine. You really need to know what your system needs. So I've done a bunch of power supply optimization and layout on iPhone systems. And when you have a processor in your phone that's pulling 20 amp pulsed load, you really have to have a super fast response. And you also need it to be really efficient because that thing runs off a battery and everyone's going to be mad at you if your battery drains really quickly. And so, you need to take those things into account. If you don't have fast pulse loads, then you probably can use a lower switching frequency, and that switching frequency, reducing the switching frequency, gives you efficiency gains to a certain extent because switching losses when the system transitions from conducting to not conducting, you have a lot of efficiency losses on all of those transitions. And so that's one of the reasons why a lower switching frequency will help you out there. I'll just say real quick, there are a bunch of other modes that bucks work on. And so you could see there's pulse frequency modulation, there's pulse width modulation, there's different schemes that bucks use, and that's relating to the different part choices that you can make. And many parts actually transition between different modes of operation across the load range. You saw the chart that Nico put up earlier, the efficiency curve of this buck. It was really low at low loads. One of the reasons for that is I think this is a fixed frequency buck. You want your buck, if you want it to be really efficient, to be able to transition to different states at lower loads or across the load spectrum. it's been a while since I did this, but I did a bunch of characterization on usually. So this buck has one frequency mode, fixed frequency mode.
Mhm.
It probably has some form of pulse skipping, and that's sort of like a pseudo frequency modulation scheme. But I worked on bucks in the past that had 5 different zones of operation, and so we had to like check all of the different transitions between these modes and make sure they're okay. There's pulse frequency mode, pulse width modulation, there was pulse amplitude modulation, and if you do much radio frequency communication or antenna stuff, you'll recognize those. Those are the same methods that we use for communicating across radio spectrum, and so it's kind of cool that it's all the same thing.
It's not part of the like of this conversation, but I imagine that also affects. So while you gain on potentially more efficiency, it might become a nightmare in terms of EMI testing and passing certifications. Like if you have like a bunch of different switching modes and frequencies, you can need to accommodate for all of that while you design in order to pass a certification for your end product.
Yeah. EMI testing is a whole other EMI EMC, whole other, like we could do 8 sessions on that.
Spectrum for EMC as well. Yeah, exactly. So if people are interested in us doing another session on like EMC and how to pass certification, stuff like that, like let us know either in the comments, in the chat, or reach out to us. So we're always looking for ideas on future sessions. So if any of you has interest in that or any other topic, let us know.
Let's so we talked a lot about the schematic. Let's talk a little bit about the layout. So I'm just going to go over to the layout tab here. All right. So component selection, I think, is the biggest way to change your efficiency and make sure that you're getting the right characteristics for your system. But you can really mess that up in layout. You can choose all the right components, but you can still have bad efficiency because of your layout, or you can have instability. I think this is one of the things that junior engineers have a really hard time with, is understanding the placement importance, especially with power supplies. Generally, when I make a board, I spend like a huge amount of effort on the placement of the components, and then the routing after that point should be really easy because everything should be in a nice line. You should have clean routes between everything, and that's great from a layout usability perspective and keeping it simple. But it's also really important for the efficiency of your system.
So in terms of layout, how would you? Sorry to interrupt, but I think that's a good point. So in terms of layout and like sort of positioning components, so can you like quickly walk us through like what do you position first? What do you position after? Like first, second? Like what do you prioritize when you position stuff? So in which order? I guess it have to be like a whole session about that, because I know you can about that, but like what, like roughly, what do you position first, and then what comes after?
Yeah, we should do a whole session about that. That'd be really great. So I'm just going to jump back to the schematic really quick, and then I'll talk you through on the schematic what I do, and then we can talk about how that was done in this layout. So I like to place everything in a group first, either on the board or off the board, and then I group all my components together, and then I move them as blocks around the system. There's always a specific order that I follow. Generally, I'll do the input capacitors first. So we have C6 and C7 over here. And you want to focus on the pathways that have the highest impact in terms of stability first, and then efficiency. If your buck isn't stable, then you don't care at all about efficiency because it doesn't work. And so the paths that have the highest impact on stability are your input cap. You want that to be as close as possible to be in. And so I place those first. Second thing I place is this output pathway. And I start with defining a very clear output path for my diode and my inductor. This boot cap is important, but it's not quite as critical as the other things. output cap, you need it to have a small loop area with respect to the IC ground. Otherwise, you'll have instability. And then the other thing that's really, really critical is your feedback path. This is what this is how the controller inside this IC knows what to do to the internal FET in order to give you a fixed output voltage. So this needs to be a really clean path. This you need to make sure that this feedback route is very clean. And you also want to make sure that there's no aggressors, like other signals that are switching nearby it that are going to impact it. You want it to be a little, this is called the switching node here, between the IC and the inductor. You want this switching node to be away from everything that's sensitive. This is one of the highest sources of noise on a system that has switching power supplies, is this node right here. You need to be really careful about that. After the inductor, it's much, much, much cleaner. This is the node where the FET is switching on and off, and you're going to see almost zero volt to supply volts swing on this. So that's some of the things on the schematic. I'm going to jump back to the layout real quick.
So it's just to recap. So you said so it's IC first, then we have the input decoupling taps, and then you have sort of the output block, so the diode, the inductor, and the capacitor, and then right after that the feedback loop.
That's right.
So in this case will be R2,
right.
R3, what this one that I forgot the name, and back. Okay, gotcha.
And so I just want to talk through that real quick, that same question over here. I placed you can see the input capacitors here on the left. And then that's leading straight to this V-in pin. We have our diode here. This has a clean path. I think this is supposed to be, this middle node is supposed to be connected. That's the E pad. And then one of the other things that I make sure to accomplish in my placement is that I have a small loop area from my controller. The PH is a switch node here. I want to clean a small loop from the switch node all the way around back to the system ground. And so that's not connected here, but it should be, and we'll fix that. Lots of people do this in a straight line. So they'll have the diode coming out, and then they'll put the inductor after that, and they'll put the capacitor on the end, and then some other smaller capacitors out there. That's fine, but you'll probably have some instability issues across frequency and load because the parasitics of this loop are higher. If you have a higher loop area, that has a higher inductance, and so your response timing will be slower. So your system can respond slower to changes in the feedback node. If the feedback node changes all of a sudden, and if it's oscillating back and forth, and your response time is skewed because of the inductance of your loop, you'll go unstable and you'll lose regulation. And so instead of getting 3 volts, you'll get like 3.2 or 3.3, and you don't want that. That'll hurt some of your ICs down the way. So that's how the placement relates to that.
So in terms of sort of efficiency itself, what would you say are the sort of the two, three main points that that you need to keep in mind? And if people are interested, during the Q&A session, we can also talk about a little bit more about the loop area, EMI, switching frequencies and stuff like that. But in terms of specifically efficiency, what would be the 2-3 things that you absolutely need to be careful with?
Yeah, I would say that the biggest thing is your resistive losses along the way. And so DCR is how you define that, your DC resistance of your different pathways here. It's you don't have literal resistors in the way, but you have copper traces, and those copper traces have resistance. That's why it's parasitic resistance, or DCR, of your traces. And so your input path here, you want this to be very wide. You also want your switch node to be very wide. This is the node that's oscillating back and forth. And so in that oscillation, you see a lot of switching losses. And so you'll burn energy with all of the current that's traveling through this path. That's just DCR of all of these components, right? So your inductor is just a coil of wire, and that coil of wire has a particular DCR. You want to make sure you have a low DCR inductor. at least for its particular inductance value. This is a huge trade-off because you want a small inductor because you want your products to be a reasonable size, but that directly impacts the DCR of your inductor, because the smaller core wire is going to give you that smaller package, and smaller core wire is a higher resistance. You want very strong connections to power and ground, and so this is sort of a mock layout, and so it doesn't have traces coming in to supply this power. But you would expect several vias to connect to this. I think this is only a 0.5 amp, 500 milliamp output buck, and so you don't need these things to be so wide for this type of a situation. But and as well as your output, and you want very clean ground connection that'll also add to your efficiency loss, because the ground, this is something that people don't worry about enough. I think people worry about the high side, the current going through, but you think that as soon as it hits ground, it's safe and you don't have to worry about the width of that ground path. But that's half of the battle. The current has to go back and get back to its source. So maybe that's a battery or a connector or whatever, but you got to get it there as efficiently as possible. Otherwise you're losing energy there.
Kerry, there's a question in the chat around the relationship between frequency and the inductance that you want to choose there. Just like in terms of if you're operating at a higher frequency, does that correspond always to a smaller inductor, or are there cases where that might not be the case?
I think almost always that's the case, but it depends on a couple of other things. Higher frequency equals smaller inductor. Yeah. Higher frequency equals smaller inductor typically because when you have a higher frequency, your inductance value needs to be lower because you're delivering energy more constantly. Higher frequency signal contains more energy in it. And so we were talking earlier about how the inductance value is the multiplier that turns that charge movement into voltage. And so for a given charge movement, you'll get a higher voltage out of it. And that is more energy. You can also get more energy out of your system by increasing the switching frequency, which gives you more energy per unit time. And so then you need a lower inductance value to get a particular voltage out of it. And so that's how that relates. You will still always get a more efficient system with a physically larger inductor because that will have lower DCR. And yet there are all of these other secondary considerations, like if your inductor has too low of DCR, maybe your controller isn't designed to handle that type of inductor. And so maybe it has some loop stability assumptions in place about the resistance of your inductor. And so you always want to kind of double check those things first. If you had an inductor that had 0 DCR, maybe that system would actually go unstable. So that's one reason to read the data sheet and really use very specifically what they recommend. That's a good question.
Last question that just some reach out to me here. So what about like RV as a no, or is it fine? And when we're like in the input or output paths, where is fine to add vias, where it isn't fine to add vias? If you have to add them or change layers, what would you do?
Yeah. That's a great question. So I would keep the power supply local layout very clean. I try to place my components for the power supply layout so that I can route all of it on layer 1, or one layer, like any layer, it doesn't actually matter. Because that will give you the simplest, most efficient layout and the smallest loop area. It's also great because then your area around it and underneath it is very clean. I'll just make one quick comment that you want to make sure that you don't place anything sensitive underneath the inductor, because that is shooting electromagnetic noise through the board, and that can actually pass through. A lot of people think that if you have a ground plane underneath the net, then everything below that ground plane is safe. That's true for electrical interference, but it is not true for magnetic interference. And I've debugged a lot of projects where that was actually causing an issue. So you can via anywhere along this path. I would say that on your input, you want a fixed input location that's before your capacitors. You don't want to via up in between your capacitors and your system and then go to the capacitors. That doesn't make sense. You'll lose your high frequency decoupling if you do that. And that's important for loop stability. You can also via anywhere in your output capacitor path, I would generally recommend that you do it after your output, your bulk. This is the bulk capacitor. Typically, I would see another smaller capacitor on the output here, like a 0.1 or a 0.1 microfarad. Sometimes you also have picofarad capacitors. That's so you have a higher frequency response in your feedback path, and you can shuttle some of that higher frequency noise through this loop, and that'll help you get better stability. The place that I would not via is the switching node, because that will create noise everywhere else in your system. And a via, especially a stub via, like say if you have a 4-layer board and you're transitioning the switching node to layer 2, that through hole via is going to go all the way to the bottom. It's going to go through the entire board, and that's going to radiate. That's going to be an antenna. You definitely don't want that. That's going to be horrible for EMI. I did use vias on the switching node in iPhone designs, but that's because we were using stacked or micro vias, and my switch node could be on layer 1 and also layer 2. And those vias stopped at layer 2, and I used shielding on layer 3 and layer 4 in order to compensate for that.
It's something that some people miss at sometimes, is that like even vias have a limited amount of current that they can carry. They also have their inherent resistance. So like that will also impact how efficient your circuit is. Like regardless of like apart from EMI, also they can carry a limited amount of current.
That's right. Yeah, and so I think the rule of thumb for through-hole vias is about 2 amps per via. This is a 500 milliamp buck, and so you would only need really 1 via. You could reduce your resistance, your DCR, by using more vias. More vias also reduces your inductance. Vias add a decent amount of inductance because they're just like wire segments, and so you want to minimize your inductance as well. So you have a clean feedback feed path. Real quick, why that matters is because that inductance will slow your response time in the same way that this inductor is storing energy in order to create voltage at the output. The inductance of the via will store energy, and that slows that energy's travel in order to get into this controller. And so that's why you worry about, I don't know if I'm allowed to talk about this, but I did a power supply and SoC combo design on iPhone many years ago, and the path to the IC, I thought it was totally fine, but it was kind of a long path, and that introduced a lot of inductance, and we actually couldn't hit the high perf states of that SoC and get the maximum performance out of it because of the inductance of that path. And so we had to go and like rejigger our whole design to fix it. That was on a development board. We wouldn't make that type of mistake on the actual product, I promise.
So we have another question here. So we're like almost at time. We're sort of basically in the Q&A section of the event. We might get like a few minutes over time if we have a ton of questions. So if you really drop them in the chat. But I just want to ask if like, I'm not sure that, John, that you're talking about like shielding around the inductor or like having a shielded inductor, if that helps with interference, or
what's the difference, shielding around the conductor versus a shielded inductor?
Okay.
Yeah, not a ton. They're very similar. And so shielded inductors, you will have a shield that's built into the package of the inductor itself. Maybe we could even go to do we have a 3D view? I know that we have a 3D view, but I want to know what this inductor looks like. Yeah. And so it'll be built into the top of it. The main difference between shielded inductors and shielding your inductors is the thickness that's possible of the shielding and the distance between it. We know that electromagnetic radiation falls off in terms of power with a r squared distance, or the square of the distance. And so if you're shielding right next to your inductor, that shielding is going to have less overall effectiveness because it's so close. And so if you have some distance for that energy to fall off before it hits the shield, that's going to help you quite a lot. There's also, magnetically saturating the material. And so if you have the material further away, the shield will be less likely to saturate and therefore lose its efficiency, lose its effectiveness. And the other difference is materials. There's only a particular set of materials that people typically use to create inductors because of the component manufacturing process. And so you have different options when you're making the shield yourself. We used to use, I think, this material called mu metal, which is a super high mu material, and you can use that for shielding in really thin sections because it's I forgot what mu actually relates to. I'm sure Jared could let me know. I think it's permeability or permittivity. It's one of those things. But when you have a really high,
it's permeability. Permittivity is the same thing, but for electric fields.
Okay. Thank you, physics consultant here. And so when you have a really high permeability, that's what allows you to block that magnetic field coming through it.
Have all the questions in the chat been addressed? There's just a couple that came in here.
John is asking about mu metal and ground planes.
Isn't mu metal sometimes used for antenna ground planes? Possibly. I bet you that's used to, if you're using an antenna that's not part of the PCB, like if you're using a Flux antenna or a chip antenna, possibly you want to change the ground in the environment that the antenna will experience. And so you'll want to tweak that, and mu metal is a really good way to tweak that and channel that field into a particular direction.
It's not cheap or particularly fun to work with, I will say. So not a great choice for your average design.
DIY.
Yeah. No, would not recommend.
Hey, I just want to give us a time check. We're basically at time here, but maybe we could just stick around for anyone who wants to keep asking questions. But I think we should probably wrap up.
Yeah, I was just going to ask to answer a question that was left here and answered. It's not related to this, but it asks if we provide some sort of fabrication services. We don't. We have templates for manufacturers that you can just basically clone, and they will have all the characteristics that manufacturer can do. So you don't have to do that your own. But we as Flux, we just developed the ECAD tool. So you'll need to manufacture that on your own. Of course, we can help you again with templates and stuff like that, but not with the manufacturing. All right. So yeah, thanks, Jared. Jared is dropping some interesting links. So YouTube channels, like our YouTube channel, sort of some third-party channels as well, our Slack community. And feel free to continue the conversation there. We're all all the Flux team is in Slack as well. And just one more minute, we are running a competition that is a energy harvesting circuit competition that I'm gonna just paste in the chat. So basically, if you design any sort of energy harvesting circuit in Flux, and you apply for this competition, which is due date is February 28th, we have some prizes there. Very interesting. If you're trying out Flux, you can also get some prizes out of that. So if you have any questions, feel free to join our Slack community. We have a competition channel there. Let us know if you plan to build something, if you're building something. We'll be glad to help you out. We have a ton of templates and parts and stuff like that you can use. So yeah, that is everything. This whole session has been recorded, and I'm gonna share with all of you via email.
Can I ask one last thing?
Yep.
What about selecting components and optimizing the design if the buck converter is output voltage is variable?
Yeah, that's a good question. A lot of the core circuitry a lot of the core philosophy will stay the same. And so you need to optimize the same things. You just need to make sure that your components will work over a larger range. And so what you can do, I think Edwin mentioned this earlier, is you can use LT Spice, and you can pick the lowest voltage and you can pick the highest voltage and simulate at both of those voltages. I think that's something that we'll eventually be able to accomplish in Flux as well. I think we can do some of those things now. One of the things that I do when it's a wide input or output range is I find an IC where they have a model in the datasheet. They have a recommended circuit that includes that entire voltage range, and then I use exactly their components. It's not a hack so much as it is just keeping it simple. I found that when I try and go and do the math to cover a wide voltage range, there's something that the manufacturer knows that I don't. There are some concerns that I'm not aware of that they take into account. And so typically I trust what they do. And if I have a part where I have to go through that math and they haven't given me a circuit that they know will work, then I go and find a different part that does. That's how I try and keep the system very safe. But you could go in if you wanted to optimize the circuit that they give you. You can go in an LT spice and you can optimize the same thing. You can optimize the DCR. You can, of the inductor, you can change the switching frequency. Often bucks will have, you can toggle between the different switching modes, and so you can find a switching mode that has higher efficiency. There's a lot of tricks there, but I like to start with a circuit that's very stable.
Okay, thanks.
Yeah, for sure.
Right. I think that's it then for today. Again, like if you have any questions after the session, we're all in Slack, Kerry's in Slack as well. So feel free to join there and let us know if you have any questions, and if you have a specific topic for the next session that you want us to do, we'll be happy to do it. All right. Thanks everybody.
Thank you so much. This is
Thanks for
awesome.
joining.
Woohoo!
Thanks.